Hello, namaste, konnichiwa, welcome to Sunny Sensei. In today's lesson, we will be learning trigonometry. I'll cover all the important concepts that you need to pass your class 10th exam. The lesson is divided into 6 sections. And along the way, we will pause, add challenge stations, interactive stops where you will solve problems and apply what you have learned. Alright, let's get started with section 1 with this extremely important question. Why trigonometry? Why should we study it? Obviously, to pass the exam, but there is much more to trigonometry than this. Trigonometry can be used to solve some very challenging real-life problems. How far is the moon from the earth? What is the height of Mount Everest? Trigonometry is certainly not the only way to answer these questions, but it can definitely make things a lot easier. Let me show what I mean with an example. Imagine this. You are walking the streets of Tokyo and suddenly you come across this magnificent structure, the Tokyo Sky Tree. How tall is this tower? Is the first question that pops in your mind. Not a tough problem to solve, right? Just climb to the peak of the tower and extend a super long measuring tape to find the height. Simple. But life is never easy. Heights. Yes, you are scared of heights. So climbing a tower is a big no-no. But hold on, you have another idea. You pull out a powerful laser pointer and aim it directly at the base of the tower. Slowly, you tilt the pointer upward until it points to the peak of the tower. When you do this, you notice the angle between the ground and the laser pointer is 60 degrees. Then you measure the distance from where you are standing to the base of the tower. It is exactly 366 meters. What else do we know? The tower is standing vertically above the ground. So this angle, the angle between the tower and the ground, should be 90 degrees. Triangle TBM is a right-angled triangle. Let me label the height of tower TB as h. So how will you find this height h? Remember, no trigonometry, no sine, no cos, nothing. Absolutely no trigonometry. Pause the video and give it a try. Alright, are you done? Perfect. Please share your solution in the comments below. I would love to see how you handle this problem without using trigonometry. Now let me explain my approach to this problem. I started with the right angle triangle, PQR, where angle PQR is 90 degrees. I also made sure that one of the other angles, angle PRQ, is 60 degrees. This is my triangle. You can pick any triangle you like. Just make sure it meets two key conditions. It has a 90-degree angle and one of the angles is 60 degrees. You should give it a try with your own triangle. Let's see if we end up with the same result. For this triangle, PQ comes out to be 13 centimeters and RQ is 7.5 centimeters. These dimensions could be different for your triangle. It's quite easy to see that triangle TBM is similar to triangle PQR. Why? Well, we have two pairs of equal corresponding angles. First, angle TMB and angle PRQ are both 60 degrees. Second, angle TBM and angle PQR are both 90 degrees. So, using the AA criterion for similarity, we can confidently say that triangle TBM is similar to triangle PQR. Now, for similar triangles, the ratio of corresponding sides is equal. So, for these two similar triangles, we have TB by PQ equals MB by RQ. But wait, how did we figure out which sides are corresponding? It's actually pretty simple. Just look for the sides that are opposite to the same angle in both the triangles. In this case, side TB in triangle TBM corresponds to side PQ in triangle PQR because they both are opposite to the 60-degree angle. Similarly, side TM corresponds to side PR since they are opposite to the 90-degree angle. And this also means that the last pair, MB and RQ, will also correspond to each other. Oh, and by the way, the third angle in both triangles is also the same. Why? Because 180 degrees minus the sum of 60 and 90 gives us 30 degrees. So third angle is 30 degrees for both the triangles. Now let me rearrange the terms a bit and we get TB by MB equals PQ by RQ. I could have skipped this step, but this expression is key to understanding the significance of trigonometry. Don't worry, I'll come back to this later. Solving further, we have TB is the height h of the tower. MB is 366 meters. PQ is 13 centimeters. And RQ is 7.5 centimeters. The height of the tower is approximately 634 meters. Oh, and just a quick note. I have rounded the final value to the nearest integer for simplicity. Did you get the same result with your own triangle PQR? If not, what was different? Let me know in the comments section below. To quickly recap, we used the concept of similar triangles to find the height of the tower. Think of triangle TBM as the target triangle and triangle PQR as the reference triangle. The reference triangle was drawn to be similar to the target triangle, and then we applied the properties of similar triangles to calculate the length of side TB of triangle TBM. This was tedious, a lot of hard work, but we managed to find the height of Tokyo sky tree without using trigonometry. So, do we really need trigonometry? Absolutely, 100%. With trigonometry, we could have solved this problem in just a couple of minutes. Let me show you how. Take a look here. The numerators on both sides, TB and PQ, are the sides opposite the 60-degree angle in each triangle. And the denominators, MB and RQ, are the adjacent sides to the 60-degree angle in each triangle. By the way, the adjacent side is the one that's next to the angle but is not the hypotenuse. Think of it as the side that supports the angle, while the opposite side is the one facing the angle. Now coming back to our expression, we equate it to this general ratio. The side opposite the 60-degree angle divided by the side adjacent to the 60-degree angle. Here is the interesting part. You can draw a million right-angled triangles, each with one internal angle of 60 degrees, and this ratio will always remain constant. Trigonometry defines this constant ratio as square root 3. Amazing, right? In our earlier approach, we used the reference triangle to find this ratio. PQ by RQ is actually square root of 3, roughly 1.733. But trigonometry does all the hard work in the background and gives us this ratio directly. No need for the reference triangle and no need for these complex calculations. And that's all we need. Using trigonometry, we have TB equals MB times square root of 3. Which gives us the height h as 634 meters. Simple, fast and efficient. Trigonometry is indeed an extremely powerful technique. With this, we have successfully completed section 1. Well done. Now is a good time to take a short break. Come back whenever you are ready. I'll be here waiting for you. Welcome back. Let's get started with section 2. In this section, I will introduce you to the trigonometric ratios. To begin, let's quickly go through some basic terminology. Here is a right angle triangle with sides A, B, and C. The side opposite the right angle, side C, is called the hypotenuse. Now, let's mark this angle as theta. The side directly opposite to theta is side A. And the side next to theta is side B. But wait, there are actually two sides next to theta. One of them is the hypotenuse C, which we already identified. That leaves us with the other side B as the adjacent side. Let me summarize this in a simple table. For angle theta, the opposite side is A, the adjacent side is B, and the hypotenuse is C. Now here's a little challenge for you. For this angle mu, what would be the opposite and the adjacent sides be? Pause the video and give it a try. Alright, for angle mu, the opposite side becomes B, and the adjacent side is now A. The hypotenuse remains C. The hypotenuse never changes in a right angle triangle. Here is an important point to remember. The opposite and adjacent sides are always defined relative to the angle you are focusing on. They can change depending on which angle you are looking at. For instance, side A is opposite to angle theta. But when we consider angle mu, side A is adjacent to it. Now let's dive a little deeper into trigonometry. Trigonometry is simply the study of the ratios between the sides of a right angle triangle. For this right angle triangle, trigonometry will give us the ratio of sides A to B, A to C, and all the other possible combinations. Each of these ratios has a specific name and is represented by what we call trigonometric functions. But here is the key point. These ratios are always calculated with respect to a specific angle in the triangle. In our example, the reference angle is theta. Let's start with two of the most fundamental trigonometric functions, sine and cosine. Sine of angle theta, represented simply as sin theta, is the ratio of the side opposite to angle theta to the hypotenuse. For our triangle, side opposite to angle theta is A. The hypotenuse is C. So, sin theta is A by C. Next, we have cosine of theta. We write this as cos theta. Cos theta is a ratio of the side adjacent to angle theta to the hypotenuse. The side adjacent to angle theta is B. So cos theta is B by C. It's really that simple. These two ratios, sine and cosine, form the foundation of trigonometry. Just remember, sine is the ratio of the opposite side to the hypotenuse, and cosine is the ratio of the adjacent side to the hypotenuse. Master this and you are 50% done with your trigonometry. Now that you understand the sine and the cosine, let me introduce the other trigonometric functions. Believe it or not, the remaining functions are just variations or combinations of these two fundamental ratios, the sine and the cosine. For instance, we have tangent of theta, or simply tan theta. This function is the ratio of the opposite side to the adjacent side. In this triangle, opposite side is A and adjacent side is B. So tan theta is A by B. You can also express tan theta in terms of sine and cosine. It's simply the ratio of sin theta to cosine theta. Don't worry, I'll cover the proof later in this lesson. Next, let's look at the three remaining functions. Cosecant of theta or cosec²θ, secant of theta or sec²θ, cotangent of theta or cot²θ. These functions are simply the reciprocals of the three basic functions we have already discussed. Starting with cosec. Cosec is a reciprocal of sine. It's the hypotenuse divided by the opposite side. For our triangle, cosec² is C by A. Notice how this is just the reciprocal of sin theta, which was A by C. Next, we have secant of theta or sec²θ. Sec is a reciprocal of cosine. It's the hypotenuse divided by the adjacent side. For our triangle, sec² is C by B. This is a reciprocal of cosθ, which was B by C. Finally, we have cotangent of theta or cot²θ. Cot is a reciprocal of tangent. It is the adjacent side divided by the opposite side. Cot² is B by A for our triangle. Since tan theta was A by B, cot² is simply the reciprocal. Now tan theta is sin theta by cosθ. So 1 by tan theta will be cosθ by sin theta. I want to emphasize once again that sine and cosine are the fundamental or primary trigonometric functions. The others, tangent, cosecant, secant, and cotangent, are considered secondary functions. When you come across these secondary functions, just rewrite them in terms of sine and cosine, and you are good to go. With this, we have reached the final part of this section, the challenge station. We need to prove that tan theta is sin theta by cos theta. It's time to challenge yourself. Pause the video and try solving the problem. Alright, where should we start from? Well, in trigonometry, the starting point is always the right angle triangle. One of the interior angles of this triangle is theta. In this triangle, AC is the hypotenuse. It's a side opposite to the 90-degree angle. The side opposite to angle theta is AB, which we call the opposite side. Finally, the remaining side CB, is adjacent to angle theta. So it's the adjacent side. With the basics in place, let's now dive into the proof. Let's start with the left-hand side, tan theta. By definition, tan theta is the ratio of the opposite side to the adjacent side, which in this case is AB by CB. Now let's look at the right-hand side, sin theta by cos theta. Sin theta is the ratio of the opposite side to the hypotenuse, which is AB by AC. While cos theta is the ratio of the adjacent side to the hypotenuse, which is CB by AC. Simplify this and you get AB by CB, the same as the left-hand side. So, the left-hand side equals the right-hand side. And we have proven that tan theta equals sin theta by cos theta. That's it. Our first challenge station is complete. There is one more challenge before we wrap up this section. We are working with the triangle ABC, and the task is to find the values of various trigonometric functions: sin mu, cos mu, tan mu, cosec mu, sec mu, and cot mu. Challenge time. Pause the video and give it a try on your own. Alright, let's analyze the problem. From the triangle, we know that AB equals 4 centimeters and CB equals 3 centimeters. To find the trigonometric functions, we will first need the hypotenuse, AC. Here is a quick refresher on the Pythagoras theorem. In a right angle triangle, the square of the hypotenuse, AC square, equals the sum of squares of the other two sides, AB square plus CB square. So, for our triangle, AC square equals 4 square plus 3 square. AC square is 16 plus 9, or AC square is 25. Taking the square root, AC equals 5 centimeters. The next step is to identify the sides relative to angle mu. The side opposite to mu is CB. The side adjacent to mu is AB. Now let's calculate the trigonometric functions one by one. Sin mu. Sin is the opposite side divided by the hypotenuse. So, sin mu is CB by AC, which equals 3 by 5. Number 2, cos mu. Cosine is the adjacent side divided by the hypotenuse. So, cos mu is AB by AC, which is 4 by 5. Next, tan mu. Tangent is the opposite side divided by the adjacent side. So, tan mu is CB by AB. That equals 3 by 4. You can also calculate tangent as the ratio of sine to cosine. Tan mu is sin mu by cos mu, which equals 3 by 5 divided by 4 by 5. We get 3 by 4, the same as before. Next we have cosec mu. cosecant is the reciprocal of sine. So cosec mu is 1 by sine mu, which is 5 by 3. Sec mu. Secant is the reciprocal of cosine. So sec mu is 1 by cos mu, which gives us 5 by 4. Finally, we have cot mu. Cotangent is the reciprocal of tangent. So cot mu is 1 by tan mu, which is 4 by 3. And that's it. We have completed our second challenge station. Great work. And with this, you have successfully wrapped up section 2. Well done. Now is the time to take a short break. Come back whenever you're ready. I'll be here waiting for you. Welcome back. Let's get started with our next section. In this section, I will introduce the unit circle, a concept that is fundamental to trigonometry. But hey, this is trigonometry. And in trigonometry, even a discussion about the unit circle begins with a good old right angle triangle. So here we go. We have a right angle triangle, ABC, where angle ABC is 90 degrees. One of the internal angles, angle ACB, is 60 degrees. AC is opposite to the 90-degree angle. So AC is the hypotenuse. For the 60-degree angle, AB is the opposite side and CB is the adjacent side. Now that we have this triangle, let me revisit the question from where we started this lesson. Why do we need trigonometry? What can trigonometry offer us? Trigonometry gives us the ratios. The ratio of one side of a right angle triangle to another side. These ratios are represented as trigonometric functions. For example, in this case, the sine of 60 degrees is the ratio of the side opposite the 60-degree angle to the hypotenuse. Similarly, the cosine of 60 degrees is the ratio of the side adjacent to the 60-degree angle to the hypotenuse. What trigonometry does is to provide us with the values of these ratios for every possible internal angle. Pioneers of trigonometry were very smart people. To simplify calculations, they decided to use a right angle triangle where the hypotenuse equals 1 or unity. It could be 1 centimeter, 1 meter, or 1 kilometer. Any unit of length is fine. Why? Because the unit doesn't matter. Trigonometric functions are based on ratios of sides. And when we calculate these ratios, the units cancel out. The units assigned to the hypotenuse do not matter. Alright, let's now see what happens to our trigonometric ratios sin 60 degrees and cos 60 degrees when the hypotenuse AC is 1. With the hypotenuse equal to 1, sine of 60 degrees is equal to the length of the side opposite to the 60-degree angle. Similarly, cos of 60 degrees is equal to the length of the side adjacent to the 60-degree angle. Now we have the measurements of all three sides. The hypotenuse is 1. The side opposite to the 60-degree angle is sine 60 degrees. And the side adjacent to the 60-degree angle is cos 60 degrees. In this example, our reference angle is 60 degrees, but we could have used any other angle of our choice. To make it more general, let's replace 60 degrees with theta. The hypotenuse is still 1. The opposite side will now be sin theta, and the adjacent side will now be cos theta. This is an extremely important conclusion. Now let's go one level deeper. We map this triangle to the xy plane. Here's a quick refresher on this two-dimensional coordinate system. The horizontal line is the x-axis and the vertical line is the y-axis. The intersection of the x-axis and the y-axis is the origin at 0, 0. Now, let me label the origin as point O. The x-axis and the y-axis divide the plane into 4 quadrants. We start with the top right, quadrant 1, and move counterclockwise to quadrant 2, quadrant 3, and quadrant 4. To quickly recap, with the hypotenuse equal to 1, the opposite side is sin theta and the adjacent side is cos theta. Now, let's focus on this point P. What are the coordinates of point P? In the x direction, it is cos theta, and in the y direction, it is sin theta. So, the coordinates of point P are cos theta, sin theta. Point P is extremely important. It contains all the information we need to figure out the trigonometric ratios. The x-coordinate represents cos theta and the y-coordinate represents sin theta. These two, sin and cos, are the primary trigonometric functions. All the others, tan, cosec, sec, and cot, can be derived from these two. Everything we need is neatly bundled into the single point P. We keep only the hypotenuse and get rid of the other two sides from the diagram. As theta increases, the point P moves in the anti-clockwise direction, tracing a circle. The radius of the circle is OP, which equals 1 or unity. This is our unit circle. Alright, what next? How do we make sense of this unit circle? Before diving deeper, let's quickly revisit some basics about the XY coordinate system. There might be some repetition here, but please be patient. This is important. First, the origin. At the origin, both the x and the y coordinates are 0. So, the origin is 0, 0. Just remember, the first number is the x coordinate and the second one is the y coordinate. Next, the coordinate lines. The x-axis is positive to the right of the origin and negative to the left. Similarly, the y-axis is positive above the origin and negative below it. Alright, now let's look at point P. OP is the line connecting P to the origin. The angle between OP and the positive x-axis is what we are calling theta. This angle will be positive. The rule is simple. Angles measured in the anti-clockwise direction are positive. Angles measured in the clockwise direction are negative. For example, take a point Q in the 4th quadrant. The line OQ makes an angle of 30 degrees clockwise with the positive x-axis. Since it's clockwise, we write this as minus 30 degrees. If you measure the same angle in the anti-clockwise direction, it would be plus 330 degrees. And here's the interesting part. Minus 30 degrees and plus 330 degrees both describe the same point on the xy plane. So negative 30 is same as positive 330. This is an important conclusion. So keep this in mind. Oh, and one more thing. Did you notice that Q in this example is not on the unit circle? That was intentional. These rules about angles work for any point in the xy plane, not just the unit circle. The unit circle is simply a special case. Last, but definitely the most important, we have the four quadrants 1, 2, 3, and 4. Quadrant 1 is from 0 degrees to 90 degrees. To be precise, it includes 0 degrees, but not 90 degrees. Quadrant 2 is from 90 to 180 degrees. Quadrant 3 is from 180 to 270 degrees. Finally, quadrant 4 is from 270 to 360 degrees. You might be wondering, why is the top right quadrant considered the first one? Why can't we have the x-axis positive to the left of the origin and negative to the right? These are great questions. And my answer is simple: conventions. Mathematicians around the world have agreed to these rules to avoid confusion. Consistency is important. Think of it as a language of mathematicians where each term has a specific meaning that everyone agrees on. Let's now move back to point P. The angle between OP and the positive side of the x-axis is theta. Now here's a question for you. Can you figure out the sign, positive or negative, of sin theta, cos theta, and tan theta for this point? Here's a hint for you. P is in the first quadrant. Take your time, pause this video and give it a thought. Alright, point P is in the first quadrant. We will start by looking at its coordinates. The x-coordinate for P is positive. And remember, the x-coordinate represents cos theta. So, cos theta has to be positive. Next, the y-coordinate for P is also positive. And since the y-coordinate corresponds to sin theta, that means sin theta is positive too. Finally, tan theta is simply the ratio of sin theta to cos theta. With both sin theta and cos theta positive, the ratio tan theta must also be positive. Let's now move this point to the second quadrant. What do you think will happen to the signs of sin theta, cos theta, and tan theta in the second quadrant? Once again, pause the video and give it a try. Alright, here is the explanation. For point P in the second quadrant, the x-coordinate is negative. X-coordinate is cos theta, and this means cos theta will be negative. However, the y-coordinate is positive because we are above the origin in the y direction. And as the y-coordinate represents sin theta, this means sin theta will be positive. Now, tan theta is a ratio of sin theta to cos theta. A positive value divided by a negative value results in a negative number. So, tan theta will be negative in the second quadrant. Next, let's move to the third quadrant. For all points in this quadrant, including point P, both the x and y coordinates are negative. Since sin theta corresponds to the y coordinate and cos theta corresponds to the x coordinate, both sin theta and cos theta will be negative. Now, tan theta is a ratio of sin theta to cos theta. A negative divided by negative gives a positive. So tan theta will be positive in the third quadrant. Finally, we reach the fourth quadrant. Here, the x-coordinate is positive, which means cos theta is positive. However, the y-coordinate is negative. So, sin theta is negative. Since tan theta is sin theta divided by cos theta, a negative divided by a positive results in a negative. So, tan theta will be negative in the fourth quadrant. For the other trigonometric functions, finding the sign is pretty simple. Cosec is the reciprocal of sine, so it will have the same sign as sin theta. Similarly, sec is the reciprocal of cos, and cot is the reciprocal of tan. So sec and cos always have the same sign, and cot and tan also share the same sign. I have added one more row to this table to include cosec theta, sec theta, and cot theta. Cosec is aligned with sine, meaning they share the same sign. Similarly, sec aligns with cos, and cot aligns with tan. Last, but the most important point, don't try to memorize this chart. Just visualize the unit circle on the xy plane, and you should be able to figure out the signs of all trigonometric functions easily. A quick recap. For quadrant 1, x and y both are positive, plus plus. For quadrant 2, x is negative and y is positive. Quadrant 2 is minus plus. Quadrant number 3, x and y both are negative. It is minus minus. Finally, quadrant 4, x is positive and y is negative. For quadrant 4, we have plus minus. Don't forget, x coordinate is cos and y coordinate is sine. That's all. Now that we understand the signs of the trigonometric functions, the big question remains. How do we find the actual numerical values for these functions? It's actually quite simple. Start by taking a ruler and measuring the x coordinate, x, and the y coordinate, y, for the point P on the unit circle. We know the x coordinate corresponds to cos theta, and the y coordinate corresponds to sin theta. Once we have sin theta and cos theta, we can easily calculate the rest of the trigonometric functions. For example, tan theta is sin theta by cos theta, and that's it. We have got all the trigonometric values we need. For some values of theta, it is even simpler. We can use our understanding of the coordinate system and basic geometry to easily find the values of trigonometric functions. Here's a table with various values of theta. Notice that I have explicitly marked the positive theta values with a plus sign, indicating counterclockwise movement. Counterclockwise is positive. We will now find the sine, cosine, and tangent for each value. As always, pause the video and try to fill out the table by yourself. You should not only fill the correct values, but also make sure you understand how you arrived at each value. Let's start with theta equal to 0 degrees. At 0 degrees, point P lies on the x-axis. The x-coordinate is plus 1. The 1 comes from radius of the unit circle, and the plus sign indicates the direction. Since point P is on the positive side of the x-axis, we have cos 0 degrees equal to plus 1. As point P lies on the x-axis, the y-coordinate is 0, which means sine of 0 degrees is 0. Now let's skip ahead to theta equal to plus 90 degrees. Here P is on the y-axis. The y-coordinate is plus 1. Point P is on the positive side of the y-axis. So, sine of plus 90 degrees equals 1. The x-coordinate is 0. So, cos plus 90 degrees equals 0. Next, let's move to theta equal to plus 180 degrees. Now P is back on the x-axis, but on the negative side. The x-coordinate is minus 1. So cos of plus 180 degrees equals minus 1. The y-coordinate is 0. So sine of plus 180 degrees equals 0. For theta equal to plus 270 degrees, we are now on the negative y-axis. The y-coordinate is minus 1. So sine of plus 270 degrees equals minus 1. The x-coordinate is 0. So cos plus 270 degrees equals 0. Finally, at theta equal to plus 360 degrees, P returns to the positive x-axis. We are back to where we started from. The x-coordinate is plus 1. So cos of plus 360 degrees equals plus 1. The y-coordinate is 0. So sine of plus 360 degrees equals 0. Plus 360 degrees is equivalent to 0 degrees, meaning sine of plus 360 degrees equals sine of 0 degrees, and cos of plus 360 degrees equals cos of 0 degrees. This pattern highlights a key property of the unit circle. Trigonometric functions are periodic with a period of 360 degrees. Their values repeat every full cycle around the unit circle. Make sure to fully understand this property of trigonometric functions. This is one of the foundational concepts in trigonometry and will definitely help you solve problems more efficiently. Before we move on to other values of theta, here is a quick challenge for you. Can you figure out the values of tan 0 degrees, tan of plus 90 degrees, tan plus 180 degrees, tan plus 270 degrees, and tan plus 360 degrees? Pause this video and give it a try. Alright, we already know that tan is sine divided by cos. Since we know the sine and the cos values, finding tan is pretty straightforward. For tan 0 degrees, it is sine 0 degrees divided by cos 0 degrees, which is 0 divided by 1 equals 0. For tan plus 90 degrees, it's sine plus 90 degrees divided by cos plus 90 degrees, which is 1 by 0. We can't divide by 0, so tan plus 90 degrees is undefined. For tan plus 180 degrees, it's sine plus 180 degrees divided by cos of plus 180 degrees, which is 0 divided by minus 1 equals 0. For tan plus 270 degrees, it's sine plus 270 degrees divided by cos plus 270 degrees, which is minus 1 divided by 0. Again, division by 0 is undefined. So tan of plus 270 degrees is undefined. Finally, for tan of plus 360 degrees, it's sine of 360 degrees divided by cos of 360 degrees, which is 0 divided by 1 equals 0. And we are done. Let's now move to theta equal to 30 degrees. What is the value of sine plus 30 degrees, cos plus 30 degrees, and tan plus 30 degrees? Pause the video and give it a try. Alright, we are taking a slightly different approach here. We move clockwise 30 degrees from the positive side of the x-axis and mark this point as R on the unit circle. This angle is minus 30 degrees, negative because we moved clockwise. Also, OP and OR are both radii of the unit circle. So both equal 1. Now what are the coordinates of R? The x coordinate is cos minus 30 degrees and the y coordinate is sin minus 30 degrees. Before we go any further, let me quickly revisit some basics. Do you remember that the signs of the x and the y coordinates depend on the quadrant? In quadrant 1, both x and y are positive, plus plus. In quadrant 2, minus plus. In quadrant 3, minus minus. And in quadrant 4, plus minus. Now look at points P and R. For both these points, the x coordinate is positive and equals OQ. This means cos of minus 30 degrees should be equal to cos of plus 30 degrees. So we can rewrite the x coordinate for point R as cos of plus 30 degrees. For the y coordinate, it is positive for P, but negative for R. Now we also have triangle OPQ that is congruent to triangle ORQ. You can easily prove this using ASA criterion for congruency. This means length of side PQ equals length of side RQ. So, y coordinates for P and R have same lengths but different signs. What does it mean? It means that sine of minus 30 degrees equals minus sine of plus 30 degrees. We have learned something very useful here. Sine of minus theta equals minus sine of theta. Cos of minus theta equals cos of theta. And this is true for all values of theta. I know this is a lot of new information. If you need a break, go for it. But before you proceed, make sure that you go back and have a relook at the explanation. This is an important concept. Spending some time on revision will definitely help. Back to our problem now. Look at triangle OPR. It's an equilateral triangle. Why? Because all its internal angles are 60 degrees. So, side OP equals side PR. But we are talking about the lengths of the sides here. This means we only care about how long the side is, not the direction. In other words, we are talking about the magnitude of the sides. That's why the correct way to write this is magnitude of OP equals magnitude of PR. We can replace PR with PQ plus QR. The length of OP is 1. The length of PQ is sine of plus 30 degrees. And the length of QR is also sine of plus 30 degrees. Notice that even though QR is pointing downwards, we are using its length. So we ignore the negative sign here. Solving further, we get 1 equals 2 times sine of plus 30 degrees. So, sine of plus 30 degrees is plus 1 by 2. We now know sine of plus 30 degrees. This can be used to find sine of minus 30 degrees. Sine of minus 30 degrees is minus sine of plus 30 degrees. That is minus 1 by 2. Sine of plus 30 degrees is plus 1 by 2. Sine of minus 30 degrees is minus 1 by 2. It is time to create some space and move ahead to triangle OQP. It is a right-angled triangle. Using Pythagoras theorem, OP square equals pq square plus oq square, or 1 equals sin square plus 30 degrees plus cos square plus 30 degrees. Since sine of plus 30 degrees is 1 by 2, we have cos of plus 30 degrees equals plus minus square root of 3 by 2. Now P is in the first quadrant, where the x-coordinate is positive. So we reject the negative value. Cos of plus 30 degrees equals plus square root 3 by 2. Cos of minus theta equals cos of theta. So cos of minus 30 degrees equals cos of plus 30 degrees, which is plus square root of 3 by 2. Cos plus 30 degrees is plus square root 3 by 2. Cos of minus 30 degrees is also plus square root 3 by 2. I want all of you to have another careful look at the process we followed to find the sine and cosine of plus 30 degrees. We used the unit circle as our starting point, and with this unit circle, we found the values of sine 30 degrees and cos 30 degrees, and also learned two important concepts. Sine of negative theta equals minus of sine theta, and cos of minus theta equals cos of theta. With these concepts, we could easily find the values of sine and cosine of minus 30 degrees. Let me emphasize, unit circle is fundamental to trigonometry. Make sure you fully understand this concept before you proceed further. If you have any doubts or questions, please feel free to add them to the comments. I'll be happy to help. Alright, let's now populate our table for theta equal to plus 30 degrees. Sine 30 degrees is plus 1 by 2. Cos 30 degrees is plus square root of 3 by 2. Tan 30 degrees is simply the ratio of sine 30 degrees to cos 30 degrees. 1 by 2 divided by square root of 3 by 2 is plus 1 by square root of 3. Moving further to theta equal to plus 45 degrees and plus 60 degrees. Here are the values. Please make sure that you confirm these values using the unit circle. The approach is similar to what we used for plus 30 degrees. If you face any problems, write to me in the comment section below. I'll be happy to guide you. With this, we have reached the final part of this section, the challenge station. Point A lies on the unit circle at an angle of 150 degrees. A. What are the coordinates of point A on the unit circle? B. Are the x and y coordinates positive or negative? C. Find the exact values of these coordinates. Please pause the video and give this problem a try. Alright, what do we have here? Point A is on the unit circle at an angle of 150 degrees. We have the unit circle, and here is point A at 150 degrees. Now we need to find the coordinates of this point. It's actually quite straightforward. The x-coordinate will be cos 150 degrees, and the y-coordinate will be sin 150 degrees. Just remember, if a point lies on the unit circle at an angle theta, then its coordinates are cos theta, sin theta. That's it. Moving on to part B. We have to find the signs of the coordinates. Point A lies in the second quadrant. In this quadrant, the x-axis is negative. So, the x-coordinate is negative. The y-axis is positive in the second quadrant, which means y-coordinate is positive. Moving to part C, we have to find the values of both coordinates. Let me make another point, A prime, at 30 degrees on the unit circle. Now look at the x-coordinate of A prime. It's cos 30 degrees, which equals plus square root of 3 by 2. Why the plus sign? Because we are in the positive x direction. The value square root of 3 by 2 is just the magnitude. The y-coordinate is sin 30 degrees, and that's plus 1 by 2. Again, positive y direction, magnitude is 1 by 2. Now let's move back to point A at 150 degrees. In the second quadrant, the x-coordinate is negative and the y-coordinate is positive. How do we find their magnitudes? Simple. The triangle ABO is congruent to triangle A prime B prime O. You should try proving this yourself. It's actually quite simple. Since these two triangles are congruent, the lengths of OB and OB prime and the lengths of OA and OA prime are equal. So, the magnitudes of the coordinates will also be the same. That means for point A, x-coordinate equals minus square root 3 by 2. Y-coordinate equals plus 1 by 2. With this, we are done with this problem. But before we move forward, let me highlight something important that we just learned. Cos 150 degrees is minus square root 3 by 2. This means cos 150 degrees is the negative of cos 30 degrees. Now, 150 is nothing but 180 minus 30. So we can say cos of 180 degrees minus 30 degrees equals minus of cos 30 degrees. In general terms, cos 180 degrees minus theta equals minus cos theta. Similarly, we saw that sine of 150 degrees is equal to sine 30 degrees. Sine of 180 degrees minus theta equals sin theta. These are important identities that you should remember and most importantly, understand. If you are comfortable with the concept of the unit circle, you can easily visualize these in your head. Remember, the unit circle is your starting point. With this, you have successfully completed section 3. Good job. It's time for a well-deserved break. Come back whenever you're ready for the next section. I'll be here waiting for you. Welcome back. Let's move on to the next section. Trigonometric identities. We'll begin with a quick recap of the identities we already know. Here we go. Sine of minus theta equals minus sine theta. Cos of minus theta equals cos theta. And then we have sine of 180 degrees minus theta equals sin theta. Cos of 180 degrees minus theta equals minus cos theta. Now can you try to figure out the corresponding identities for other ratios? Alright, tan is sine divided by cos. So, tan of minus theta becomes sine of minus theta divided by cos of minus theta, which simplifies to minus tan theta. Cosec is just the reciprocal of sine. So, cosec minus theta equals minus cosec theta. We can use the same logic to figure out the other identities shown here. Just remember this key idea. Sine and cos are the fundamental trigonometric ratios. Once you understand these two, the rest are quite easy to derive. Alright, let's now move ahead to these two identities. Sine of 90 degrees minus theta equals cos theta. Cos of 90 degrees minus theta equals sin theta. We start with the xy plane and draw a unit circle. Point P lies on the circle at an angle of theta. Its coordinates cos theta and sin theta. Now let's look at another point Q at an angle of 90 degrees minus theta. Its coordinates are cos 90 degrees minus theta and sin 90 degrees minus theta. Let me zoom in a little so you can see this better. Now focus on the two triangles. Triangle OPM and triangle QON. We can observe the following. Angle POM is equal to angle OQN. Both are theta. OP and QO are both radii of the unit circle, so they are equal to 1. Angle OPM and angle QON are also equal. Both are 90 degrees minus theta. So we have two angles and the included side equal in both triangles. That means by the ASA rule, the triangles OPM and QON are congruent. And when two triangles are congruent, their corresponding sides are equal. So we get MP equals ON and OM equals NQ. Just a reminder, we are only comparing the lengths of the sides here. You will notice I have put vertical bars around MP, ON and other sides. That's a symbol for modulus. It means we are looking at the size or length of the side, not whether it's positive or negative. Now for point P. The x-coordinate is cos theta, which is positive and equals the length of OM. The y-coordinate is sin theta, which is also positive and equals the length of MP. Moving to point Q. The x-coordinate is cos 90 degrees minus theta. This is also positive and equals the length of ON. But from earlier, we know ON equals MP. And from 2, sin theta equals MP. So we have cos of 90 degrees minus theta equals sin theta. The y-coordinate is sin 90 degrees minus theta, which is positive and equals the length of NQ. Again, NQ equals OM. And from 2, cos of theta equals OM. So we get sine of 90 degrees minus theta equals cos theta. Here are the two new ideas that we just learned. First, cos of 90 degrees minus theta equals sin theta. Second, sine of 90 degrees minus theta equals cos theta. And both of these come from the concept of the unit circle. You are not simply memorizing the formulas, you are actually seeing where they come from. That's the beauty of the unit circle. Moving to the next identity, the most fundamental in trigonometry. sin² plus cos² equals 1. This time, let's start with a right-angled triangle. One of the interior angles is theta. The side opposite to theta is A. The side adjacent to theta is B. And the hypotenuse is H. So, sin theta will be A by H and cos theta will be B by H. Alright, we have got our right-angled triangle. Now let's apply the Pythagoras theorem. The sum of the squares of the two sides equals the square of the hypotenuse. A square plus B square equals H square. Now dividing both sides by H square. A by H is sin theta and B by H is cos theta. So we get sin²θ plus cos²θ equals 1. And that's it, we are done. But before we move further, here's a challenge for you. Can you prove this identity using the unit circle? Yes, it can be done. Just stick to the basics. Moving on, this is our next trigonometric identity. tan²θ plus 1 equals sec²θ. We will start with what we just learned. sin² plus cos² equals 1. Now dividing both sides by cos²θ, we get sin by cos is tan and 1 by cos is sec. So we have tan²θ plus 1 equals sec²θ. With this, we are done with the proof. Next up, another trigonometric identity. cot²θ plus 1 equals cosec²θ. Our starting point is the same. sin² plus cos² equals 1. This time, we divide both sides by sin² and we get cos by sin is cot and 1 by sin is cosec. So we have cot²θ plus 1 equals cosec²θ. And we are done. With this, we have reached the final part of this section, the challenge station. We have to prove that 1 plus tan² x divided by 1 plus cot² x equals tan square x. Please pause the video and give this problem a try. Alright, let's start with the left hand side. 1 plus tan square x divided by 1 plus cot square x. Now, 1 plus tan square x is sec square x and 1 plus cot square x is cosec square x. So we have now sec is 1 by cos and cosec is 1 by sin. So sin by cos is tan, or sin square x by cos square x is tan square x. Left hand side equals right hand side. This is our proof. But hold on, let me prove this again using another approach. There are always multiple ways to handle trigonometric identities. We again start with the left hand side. This time we replace tan with sin by cos and cot with cos by sin. Sin square x plus cos square x is 1. This gives us sin square x by cos square x, which is again tan square x, our right hand side. We are done. Here is our next challenge. We have to prove that 1 plus tan square x divided by 1 plus cot square x equals 1 minus tan x whole square divided by 1 minus cot x whole square. Once again, pause the video and give this problem a try. This time, let's start with the right hand side. 1 minus tan x whole square divided by 1 minus cot x whole square. Now, a minus b whole square is a square plus b square minus 2ab. So applying that here, the numerator becomes 1 plus tan square x minus 2 tan x. And the denominator becomes 1 plus cot square x minus 2 cot x. I can already see the left hand side showing up here. I pull out 1 plus tan square x from the numerator and 1 plus cot square x from the denominator. We know 1 plus tan square x equals sec square x and 1 plus cot square x equals cosec square x. So now we have solving further. Now cancelling out the common parts from numerator and denominator, we are left with 1 plus tan square x divided by 1 plus cot square x. So RHS equals LHS. And that's our proof. This one's slightly tricky, right? So let me share an alternative approach. We will start with the right hand side. But this time, we won't try to match it directly with the left hand side. Instead, we will just simplify it step by step. First, we replace cot with 1 by tan. We have RHS equal to tan square x. Now let's simplify the left hand side. Replace cot with 1 by tan and we get so left hand side equals right hand side with both equal to tan square x. That's our proof. We are done. And with this, we have successfully completed section 4. Thank you so much for staying with me. Now it's time for a short break. Pause the video and come back when you are ready. I'll be waiting for you. Welcome back. Let's move on to the next section, Trigonometry in practice. In this section, I'll go through some common question types and explain key terminology that you will often see in the class 10th exam. So let's get started with angle of elevation and angle of depression. Imagine you're walking through a park. Most of the time, you look straight ahead. This line of sight, parallel to the ground, is called the horizontal line. Then you notice a bird sitting on the top of a tree. Your line of sight moves upward from the horizontal to the bird. The angle between your horizontal line and this upward line of sight is called the angle of elevation. Let's call this angle A. Now if your eyes move downward from the bird to the base of the tree, the angle between the horizontal and this new line of sight is called the angle of depression. Let's call this angle B. Remember, the horizontal line is always the reference for both elevation and depression. And this horizontal line is unique for each point of observation. In this case, your eye level is the point of observation. Now let's say the bird on the top is also looking at you. What will be the horizontal line for this bird? Here it is. Parallel to the ground, but aligned with the bird's eyes. If the bird looks down at you, the angle formed between its horizontal line and its line of sight is the angle of depression. Here is something interesting. This angle is also A, equal to the angle of elevation from your perspective. Why? Because the two horizontal lines, yours and the bird's, are parallel, and the angles on the alternate sides of a transversal are equal. Quite simple, right? Now look over here. We have a yellow bird in the sky. If the bird sitting on the tree looks up at the yellow bird, that becomes its line of sight. And the angle between its horizontal line and this upward line of sight is the angle of elevation. This angle D is the angle of elevation for the bird on the tree looking at the yellow bird in the sky. Just remember, angles of elevation and depression always depend on the point of observation and its horizontal line. Alright, let's now check our understanding of what we just learned. Here is a problem for you. A pole 6 meters high is fixed on the top of a tower. The angle of elevation of the top of the pole observed from a point P on the ground is 60 degrees. And the angle of depression of the point P from the top of the tower is 45 degrees. Find the height of the tower and the distance of point from the foot of the tower. Pause the video and give it a try. Alright, we have a tower on the ground and a pole of length 6 meters on top of it. There is a point P on the ground. Angle of elevation from P to the top of the pole is 60 degrees. Now, the angle of depression from the top of the tower to point P is 45 degrees. We have parallel lines with a transversal. As alternate interior angles are equal, this angle will also be 45 degrees. We have to find the height of the tower. Let this be h. We also have to find the distance of point P from the foot of the tower. We call this d. Let me label the diagram. Now, it's time to use some trigonometry. For triangle ABP, which is a right angle triangle, tan of 60 degrees is opposite side AB divided by adjacent side BP. Tan of 60 degrees is square root of 3. AB is AC plus CB and BP is D. AC is given as 6 meters and CB is h. So we have D is 6 meters plus h divided by square root of 3. For right angled triangle CBP, tan of 45 degrees is CB by BP. Solving further, we get D equal to h. Combining these two results, we have h is 6 meters by square root of 3 minus 1. We rationalize the denominator by multiplying and dividing the expression with square root of 3 plus 1. Some simple math. And we get h equal to 8.19 meters. As d equals h, d is also 8.19 meters. Height of the tower is 8.19 meters. Distance of point P from the base of the tower is also 8.19 meters. We are done. Here is a complete list of trigonometry related skills that are tested in the class 10th exam. We are already done with the first one, angles of elevation and depression. Let's move to the next one. values of trigonometric ratios, sine, cos and tan at some key angles. Yes, you are definitely expected to know the values of these ratios at 0, 30, 45, 60 and 90 degrees. Here is the problem from one of the past exams. If sin theta equals cos theta, then the value of sec theta times sin theta is. We are given 4 options here. Please pause the video and give it a try. Alright, we have sin theta equal to cos theta. Theta has to be 45 degrees. Sin and cos both are equal to 1 by square root 2 at 45 degrees. Actually, sin and cos can be equal at other values of theta too, but we stick to 45 degrees. Why? Because the problem limits the value of theta between 0 degrees and 90 degrees. We have to now find the value of sec 45 degrees times sin 45 degrees. Sec is 1 by cos. Cos 45 degrees is 1 by square root 2. So, sec of 45 degrees is square root 2. Sin of 45 degrees is 1 by square root 2. Square root 2 times 1 by square root 2 is 1. C is our choice. Here is another problem, again from one of the past exams. We have to evaluate this expression. Please pause the video and give it a try. Let's start by plugging in the values of the trigonometric ratios. Cos 45 degrees is 1 over square root 2. Sin of 60 degrees is square root of 3 over 2. Sec of 30 degrees is the inverse of cos 30 degrees, so that gives us 2 over square root 3. Cosec 30 degrees is 1 over sin 30 degrees. Sin 30 degrees is 1 by 2. So cosec of 30 degrees is 2. Let's now simplify the expression step by step. But don't stop here. Always rationalize the denominator. So we multiply and divide the expression by 3 minus square root of 3. Carry out the algebra carefully. And we get the final simplified form. And we are done. Did you follow the same steps? Or did you use a different method? Let me know in the comments below. I would love to hear from you. Alright, this wraps up our examples for skill number 2. Knowing the values of sine, cos and tan at key angles, super important. Now let's move on to skill number 3. Understanding the definition of trigonometric ratios. This is where we go back to the basics. We need to know that sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. Tan is opposite over adjacent. These definitions are the foundation of almost every trigonometric question. Let's look at an example on this fundamental skill. If 12 cosec A equals 13, then find the value of 2 sin A minus 3 cos A divided by 4 sin A minus 9 cos A. Once again, pause the video and give this problem a try. We start with cosec A equal to 13 by 12. Cosec is 1 by sine. So, sine A is 12 by 13. Now we use this identity. Sin square A plus cos square A equals 1. Plugging in the value of sin A, we get cos A equal to plus minus square root of 25 by 169. Let's assume A is in the first quadrant, where all trigonometric values are positive. So we drop the negative sign. Cos A is 5 by 13. Let's now move back to the expression. We simply substitute the value of sin A, 12 by 13, and cos A, 5 by 13, and simplify. Three is our answer. With this, we are done with skill number 3, understanding the definitions of trigonometric ratios. Let's now move on to skill number 4, applying basic algebraic identities to simplify or solve trigonometric problems. Yes, you will need to know the basic algebraic identities such as a plus b whole square is equal to a square plus b square plus 2ab to solve problems in trigonometry. Here is the first problem. If sec theta minus tan theta equals m, then the value of sec theta plus tan theta is, we have 4 options here. Please pause the video and give this problem a try. Well, let's have another look at the question. We are given sec theta minus tan theta, and we are asked to find sec theta plus tan theta. This pattern, one sum and one difference, immediately reminds me of the identity a square minus b square equals a plus b, a minus b. Using this, we have sec square theta minus tan square theta equals sec theta plus tan theta multiplied by sec theta minus tan theta. We replace sec square theta with 1 plus tan square theta. And sec theta minus tan theta with m. Solving further, sec theta plus tan theta equals 1 by m. C is our choice. Here is one more problem. We need to simplify the given expression and choose the correct answer from the 4 options. Go ahead, pause the video and give this problem a try. Alright, here is our expression. Sin cube A plus cos cube A over sin A plus cos A plus sin A cos A. As soon as I see the sum of cubes, sin cube A plus cos cube A, I am reminded of the identity. A plus B whole cube equals A cube plus B cube plus 3AB A plus B. Notice the sum of cubes here. We use this identity and replace sin cube A plus cos cube A with We also have a square of a sum. Remember the identity. A plus b whole square equals a square plus b square plus 2ab. Using this, we simplify. Finally, sin square a plus cos square a equals 1. Our expression simplifies to 1. A is the correct choice. Before we move forward, let me show you an alternative approach. One that can help when you are stuck and unable to simplify the expression directly. We have 4 options here, and we will try to eliminate the incorrect ones one by one. Let's start by solving the expression for a equal to 0 degrees. Why 0 degrees? Because this angle often makes trigonometric expressions easier to evaluate. At a equal to 0 degrees, our expression equals 1. That means we can eliminate options B and D. Option A is 1, so we keep it. What about C? At A equals 0 degrees, option C also gives 1, so we cannot reject C. Now, I would usually pick 90 degrees next, but a quick mental check tells me that it won't help eliminate either A or C in this case. So let's try A is equal to 45 degrees instead. At A equal to 45 degrees, our expression again equals 1. But option C, at A equal 45 degrees, gives 2. So we can safely eliminate C. We are left with only one option, option A. A is our choice. Here is a list of basic algebraic identities that you should keep in mind while solving trigonometry questions. These are quite straightforward, and I'm sure you already know them, but it's important to scan each question quickly and spot where one of these might apply. Using the right identity at the right moment can make a lot of difference. With this, we are done with skill number 4. Applying basic algebraic identities to simplify or solve trigonometric problems. Now let's move on to the last skill, knowledge of basic trigonometric identities. Make sure you remember these 3 basic identities. This will come handy in solving trigonometric problems in the exam. Here is the first problem to test you on this skill. Prove that square root of sec²θ plus cosec²θ equals tanθ plus cot²θ. Please pause the video and give this problem a try. Alright, let's start with the left hand side. We know that sec²θ equals 1 plus tan²θ and cosec²θ equals 1 plus cot²θ. Notice the sum of squares over here. What comes to mind is this identity. A plus b whole square equals a square plus b square plus 2ab. To match the format, we add and subtract 2 tanθ cot²θ. This part is now a perfect square. Square of tan theta plus cot theta. Cot is reciprocal of tan. So 2 times tan theta cot theta is 2. Taking the square root gives us tan of theta plus cot of theta. The left hand side equals the right hand side. We are done. Here is one more problem. We have an assertion. If sin A equals 1 by 3, then the value of cos A is 2 square root 2 by 3. We also have a reason. For every angle theta, sin²θ plus cos²θ equals 1. We need to confirm 3 things. Number 1, is the assertion true? Number 2, is the reason true? Number 3, is the reason the correct explanation of the assertion? Based on these, we must pick one of the given options, A, B, C or D. Please pause the video and give it a try. Alright, first things first. The reason is definitely true. sin² plus cos² equals 1. This is a fundamental trigonometric identity. Now moving to the assertion. We are given sin A equals 1 by 3 and we need to confirm the value of cos A. We again start with the identity. sin²A plus cos²A equals 1. Since sin A equals 1 by 3, sin²A will be 1 by 9. Solving further, cos A equals plus minus 2 square root 2 by 3. The question states that A lies between 0 and 90 degrees. We are in the first quadrant. So we can drop the negative sign and we have cos A equal to 2 square root 2 by 3. Therefore, for sin A equal to 1 by 3, we have cos A equal to 2 square root 2 by 3. The assertion is true. Clearly, both the assertion and the reason are true, and the reason is the correct explanation of the assertion. So, option A is our choice. With this, we have reached the final part of this section, the challenge station. We have to prove that 1 by cos x minus cos x times 1 by sin x minus sin x equals 1 by tan x plus cot x. Once again, please pause the video and give this challenge a try. Alright, we will start with the left hand side. And simplify it until we reach this point. The left hand side equals sin x times cos x in the numerator and 1 in the denominator. But the right hand side has 1 in the numerator and tan x plus cot x as the denominator. How do we proceed? Simply replace the 1 in the denominator with sin²x plus cos²x. Then, to have 1 in the numerator, we divide both the numerator and the denominator by sin x cos x. We do all this so that the expression aligns with the right hand side. The key is to keep your target, the other side of the equation, in mind while proving the identity. Solving further, the left hand side equals 1 over tan x plus cot x, which equals the right hand side. This completes our proof of this identity. And with this, we have also successfully completed section 5. Good job. Now it's time for a short break. Pause the video, stretch a bit, and come back when you are ready. Welcome back. Let's move on to our final section, a recap of everything we have learned in this lesson. First, the basics. Consider a right-angled triangle with sides A, B, and C. One of the acute angles is theta. The longest side, C, is called the hypotenuse. The side opposite the angle theta is A, and the side next to theta is B, which we call the adjacent side. Moving further, here are the definitions for each of the trigonometric ratios. Sin theta is the ratio of side opposite theta to the hypotenuse. Cos theta is the ratio of the side adjacent to theta to the hypotenuse, and so on. Sin and cos are the primary trigonometric ratios. All the other ratios can be written in terms of sin and cos. For example, tan theta equals sin theta divided by cos theta. Next, we have the XY coordinate system with its 4 quadrants. In the first quadrant, both the X and the Y coordinates are positive. In the second quadrant, X is negative while Y is positive. In the third quadrant, both X and Y are negative. Finally, in the fourth quadrant, X is positive and Y is negative. A circle with its center at the origin and a radius of 1 is called a unit circle. For any point P on this unit circle at an angle theta from the positive x-axis, the x-coordinate is cos theta and the y-coordinate is sin theta. This table shows the definition of the 4 quadrants in the XY coordinate system, along with the signs of various trigonometric ratios in each quadrant. For example, sin is positive in the first and second quadrants, but is negative in the third and fourth quadrants. Class 10th exam questions usually focus on the first quadrant. However, it is still important to understand the complete picture, how trigonometric ratios behave across all 4 quadrants. Understanding the unit circle gives you the full picture, not just what the rules are, but why they work the way they do. Here are the values of sin, cos, and tan for some key angles. Make sure you know these by heart for the exam. Again, class 10th exam tends to test you mostly for values from 0 degrees to 90 degrees. But knowing a little bit extra never hurts. Here is our final and the most important slide. These are some of the basic trigonometric and algebraic identities you should know for the exam. You will be extensively tested on these, so make sure you have mastered them before the exam day. This brings us to the end of our lesson on Class 10th Trigonometry. If you enjoyed this lesson, don't forget to like this video, subscribe to my channel, and leave a comment below. I would love to hear from you. Thank you and see you again soon.